In 1970, NASA didn't just pray Apollo 13 would make it home. They built a full-scale replica of the damaged spacecraft on Earth. Astronauts trained on it. Engineers tested fixes on it. It was the first practical digital twin. Fast forward to today. A single GE jet engine tracks over 4,000 parameters per flight. 1 terabyte of telemetry data. Every single time. So what exactly is a digital twin? It's not a fancy 3D model. It's not a static simulation. It's a living, bidirectional system. A continuous feedback loop synchronized with physical reality. Today, we're tearing down the hype. We'll map the actual architecture, show you how AI shifts the game, and explain why the digital thread is the only thing keeping this from collapsing. Let's get precise. The Digital Twin Consortium defines it as a virtual representation synchronized with its physical counterpart at a specified frequency and fidelity. The concept actually dates back to 2002. Dr. Michael Greaves called it the mirrored spaces model. He refined it in 2011 to the virtually perfect, digitally exact twin. But here's where most people get it wrong. They confuse twins with simulations. Think of it this way. A simulation is like a weather forecast. It takes static inputs and predicts what might happen. A twin is the weather station. It tells you what is happening right now, and it constantly updates the forecast in real time. Technically, simulation uses episodic, one-way data. Twin ingests live sensor streams. It monitors, predicts, and acts. Bidirectional. Continuous. Take a jet engine after 10,000 flight cycles. Thermal fatigue changes the metal. A static simulation fails because it doesn't know the metal has degraded. A twin ingests exhaust gas temperature and vibration data. It recalibrates its physics models on the fly. The model updates. The prediction stays accurate. That's the difference. Twins don't exist in a vacuum. They operate at 3 distinct scales. And not all twins are built equal. First, the product twin. This is a single asset, tracked by serial number. Focus is performance and health. Tesla does this with every vehicle on the road. GE tracks its LEAP engines for $100 million annual savings. Rolls-Royce monitors entire jet fleets. Second, the process twin. This maps workflows and operations. Siemens' Amberg plant runs at 99.7% quality because the twin optimizes the assembly line in real time. DeepMind used it to slash Google's data center cooling by 40%. Third, the system twin. This scales to the ecosystem. Virtual Singapore integrates over 100,000 IoT sensors. NVIDIA's Earth 2 models planetary climate at a global scale. Here's the hierarchy. A system twin contains process twins, which contain product twins. Data flows upward. Control flows downward. You don't just build one twin. You build a hierarchy. Now here's where the engineering actually happens. You need a 5-stage loop. Stage 1 is the physical asset. Wear, environment, stress. Stage 2 is sensors and connectivity. MQTT, OPC-UA, 5G, LoRaWAN. But raw data drowns the system. Edge gateways filter and aggregate before it ever hits the cloud. Stage 3 is the digital model. The brain. You're merging CAD geometry, physics simulations like FEA and CFD, and data-driven ML models. But fidelity is a trap. Running a high-fidelity finite element mesh takes hours. Real-time twins need milliseconds. That's why you use reduced-order models. ROMs. They strip the math down to the essentials while preserving the core behavior. Stage 4 is analytics. Autoencoders catch anomalies. LSTM networks predict remaining useful life. Reinforcement learning runs what-if scenarios. Stage 5 is action. Closed-loop control. Operator alerts. Design feedback. The loop closes. The physical asset changes. The twin updates. And it starts all over again. But here's the thing. Physics-only models hit a wall. That's where AI shifts the architecture. We're moving toward physics-informed neural networks, or PINs. They bake conservation laws directly into the loss function. The AI doesn't just guess. It respects thermodynamics. Reinforcement learning then takes over optimization, pushing the twin from passive monitoring to active control. And none of this works without the digital thread. This is the non-negotiable backbone. It's the continuous, traceable data lineage from design to disposal. No thread, no twin. Just isolated data silos wearing a fancy UI. The platform landscape is still fragmented. NVIDIA owns the simulation and physics layer. Cloud providers handle the IoT integration and scale. Industrial giants like Siemens and Dassault own the lifecycle depth. You pick your stack based on your Fidelity needs. So let's lock in the architecture. Twins are bidirectional, continuous systems. You need a 5-stage loop with edge filtering and ROMs for real-time speed. AI moves you from pure physics to hybrid pins and RL optimization. And the digital thread is your only safety net. Build the hierarchy. Close the loop. Track the data. If you're architecting a twin, start with the data lineage, not the visualization. Map your sensor strategy before you touch a CAD file. Drop your stack choices in the comments. I'll break down the trade-offs in the next video. Subscribe if you want the engineering, not the hype.